this section, we'll be looking at a new term, Gibbs free energy. And this will tell us whether or not a reaction is spontaneous. Gibbs free energy is abbreviated as delta G. And if delta G is less than 0 or negative, then the reaction is spontaneous. If delta G is greater than 0 or positive, the reaction is not spontaneous. This is the term that we'll use to compare energies for biological systems, as well as engineering applications. Gibbs free energy is composed of a term for enthalpy and entropy. Let us remind ourselves. Enthalpy is delta H, and entropy is delta S. Enthalpy has to do with the heat exchange of a system, and delta S is the order or degree of order. Reminding, if delta H is less than 0 or negative, that refers to an exothermic reaction, where heat is a product. Vice versa, if delta H is positive, greater than 0, it is endothermic, and the reaction consumes heat. We also look at entropy, delta S, being greater than 0 as the system is becoming less ordered, and delta S less than 0, more ordered. So we relate these terms into this one equation for delta G. Delta G is equal to delta H minus T delta S. T is temperature in Kelvin. And enthalpy and entropy, because they're related to energy, these will be in joules or kilojoules, 1,000 joules. So we have circumstances where we can have a positive or a negative value for delta H and delta S, depending on what's happening in the system. So that would be 2 possibilities of each, or give us 4 situations or 4 types of systems. So we'll look at each of those 4 systems in the next slides. All right, this is scenario number 1, where delta G is negative at all temperatures. This means spontaneous at all temperatures. Delta H is negative, which means that it is an exothermic reaction. And delta S is positive, which means that it is becoming less ordered. Let's look at an example equation. 2 dinitrogen monoxide gas goes to 2 nitrogen gas plus oxygen gas. I know that delta H for this reaction is negative 163.2 kilojoules. So it is exothermic. I can also tell about the sign of delta S from looking at the moles of gas. 2 moles of gas on the reactant side, 1, 2, 3 moles of gas on the product side. So delta S is going to be greater than 0 because it is more disordered or less ordered is the other way to say that, on the product side. So these reactions are always spontaneous. Right, next we have situation number 2, where delta G is positive at all temperatures, so this means not spontaneous. Delta H is positive, so it is endothermic. And delta S is negative, so this would be more ordered. Looking at an example reaction, 3 oxygen gas goes to 2, this is ozone, O3 gas. Delta H for this reaction is equal to positive 285.4 kilojoules. Right, and comparing the moles of gas, 3 moles of gas on the reactant side to 2 moles of gas on the product side, so it is becoming more ordered, and delta S would be less than 0 or a negative value. So these reactions where we have positive delta H and negative delta S would not be spontaneous at any temperature. Our third scenario is where we have a mix where it's not all at all given temperatures. It will depend. So in this case, delta G is negative at low temperatures. So spontaneous at low temperature. Positive at high temperatures, so not spontaneous at high temperatures. And considering the other terms, delta H is negative, so this is exothermic. And delta S is negative, so it is more ordered. If you think about it, this makes sense because the molecules at lower temperatures, lower T, molecules are moving less. Making them less random. An example of this kind of situation would be water, liquid, going to water, solid. In other words, freezing. Delta H is equal to negative 6.01 kilojoules. So it is exothermic, but it is becoming more ordered, and this makes sense that water would freeze at low temperatures. We know that to be true instinctively. The fourth set of reactions, again, are split, where it's positive at low temperatures, so not spontaneous at low T. Negative at high temperatures, spontaneous at high temperatures. Delta H is positive, so it is endothermic. And delta S is positive, so it is less ordered. Again, that's going to favor high temperatures. So if we're looking at an example reaction, water liquid to water gas, delta H for this process is positive 40.7 kilojoules. Right, so that is endothermic, and this makes sense. Water will evaporate at higher temperatures. As we raise the temperature, more will evaporate, or more product we get. The water evaporates at higher temperatures. So in the case of 3 and 4, we have to sometimes do the math to see if the reaction is spontaneous or not. Switching tack just a little bit here, we can also think about substances within the same phase or different substances at the same phase. We know that as temperature goes up, entropy increases. It becomes less ordered. The molecules have more energy. And going back to the schematic here, you can see we talked about the lattice and the solid substances, and then this being negated in the liquid phase and the molecules are moving around more, and then the gas where they're moving with the highest energy and there are fewer molecules, there's more disorder, right? So we see entropy on the Y, and as temperature goes up on the X, entropy goes up. And so we can compare substances. And this is true experimentally. We've determined that liquid water has an entropy value of 70 joules per mole Kelvin, and water in the gas phase has an entropy of 189 joules per mole Kelvin. So as we go from solid to liquid to gas, entropy increases. And if we're comparing different substances, molar mass, as molar mass increases, entropy increases. The larger the molecule is, the more difficult it is to become ordered. So this relates to size and mass. It's more difficult to put it into that tight lattice structure to give it that solid phase, solid crystal phase. On this slide, we're going to do some calculations. Delta G is equal to delta H minus T delta S. One of the things that you need to note here is that the entropy term is in joules per Kelvin. So we want to change that to negative 0.263 kilojoules per Kelvin. We just move the decimal 3 places to the left. 1, 2, 3, or divided it by 1,000. And so we're going to use this term when we plug into our formulas. So let's look at number 1 here. Delta H, and when I convert it to this form, the delta symbol goes away and it's just shown as a capital D. All right, we see that delta G is equal to positive 115 kilojoules. That's my delta H, minus, in brackets, 298 Kelvin times negative 0.263 kilojoules per Kelvin. So I'll do that calculation first. 298 times negative 0.263 equals, so that's a negative 78 kilojoules. So I've got 115 kilojoules minus a negative 78. And I'm getting 193, positive 193 kilojoules. So my answer for this one is not spontaneous. And if I think back to my 4 situations, this is a lot like situation number 2, where we had a positive delta H and a negative delta S. So we expect it to be not spontaneous at any temperature. Okay, I'm going to move this up, and we're going to look at problem number 2. In this case, we've got 2 different temperatures here. So we're actually going to do 2 calculations, one at 298 and one at 615. And the difference here is that our delta S is the same, negative 0.263, but enthalpy is negative 115. So we're going to look at the effect at 2 different temperatures. Delta G is equal to negative 115 kilojoules minus, and then in brackets, 298 times a negative 0.263 kilojoules per Kelvin. All right, so let's do that first. 298 times 0.263 equals, and that's the same as we got above, negative 78. So we have negative 115 minus a negative 78. And we get negative 37 kilojoules. Right, so this is spontaneous. We work the second half of the problem, number 2, second half of number 2. This time, delta G is equal to negative 115 kilojoules minus 615 Kelvin times negative 0.263 kilojoules per Kelvin. All right, so we multiply 615 times a negative 0.263 equals, that's negative 115 kilojoules minus a negative 162 kilojoules. And we get positive 47 kilojoules. So this is not spontaneous. And in this case, both delta H and delta S were negative, so they would be spontaneous at lower temperatures, and we saw that to be true with our calculations. Our last example problem, we're simply going to pick which one out of the pair has the higher entropy value, and then we're going to justify. There's got to be a reason. Remember, it's going to be related to either the phase or the size / molar mass of the molecule. All right, so first we have carbon monoxide and carbon dioxide. They're both gases, but this is the heavier molecule because it has 2 oxygen as compared to 1. So that one will have the higher entropy because of molar mass. All right, we'll look at the next one. Methanol liquid and methanol gas, same molecule but 2 different phases. So in this case, the gaseous methanol would have the higher entropy, and that is due to it being at a higher phase. Right, the third example here, argon gas and carbon dioxide gas. Argon has a lower molar mass than CO2, so this one would have the higher entropy, and that is due to molar mass. Right up at the top of the second column, we have methane, CH4, and silicon tetrahydride, SiH4. Silicon is heavier, so this one, by virtue of molar mass, would have the higher entropy. Looking at the next one, they're really similar in molar mass. I think this one is 46 and this one is 44, just off the top of my head. And so from a molar mass perspective, they're not clearly different. They're both in the gas phase. But this one is much larger in size and complexity. So the CH3, CH2, CH3, which is propane, would have the higher entropy. And lastly, sodium bromide, solid or aqueous. Aqueous substances are dissolved in water, and so they are ionized and dissolved, disorganized, not in that organized crystal structure. So that one would have the higher entropy.